Hello everybody and welcome back. Today we'll be talking about how to use algebra to solve kinematic equations, which involve motion when the acceleration is equal to 0. So these are the kinematic equations. The first one, the third one, and the fourth one are the most common, although this second one is included sometimes. It'll pop up a little bit, but for this first one, really all we need to know are the first, the third, and the fourth. And so what we'll do is take a look at a little example problem. So in this case, a ball is being thrown off of a cliff that is 50 meters tall, and it lands 100 meters away in some body of water that we can see here. And so this problem assumes that there's no air resistance, and we're trying to find this velocity initial, v, how fast the ball was initially thrown off the cliff. And so to solve this, let's start off by thinking, okay, so let's redraw this diagram. So we have, it lands 100 meters away, and the cliff is 50 meters tall, and we're trying to find this initial velocity, v. But what we can notice about this velocity is that it is only going in the x direction. So it only has an x component. So what that means is if we make a table, let's say that this is the x and the y, so we can say certain things about this. So for example, the velocity in the x direction is really what we're trying to find, and the velocity in the y direction is equal to 0. Now also what we know is that delta x, the distance that it travels in the x direction, is this value of 100 meters. And in the y direction, it's traveling 50 meters. And so then if we go back to our equations, the kinematic that's going to help us the most in this case is saying that y equals y naught plus v naught t plus 1/2 a t squared. And for this side, we can also say the same thing. So x equals x naught plus v naught in the x direction, t, plus 1/2 at squared. But as you see, if it goes in the x direction, it's not experiencing any acceleration. So this is the ball. The acceleration due to gravity is only in the y direction. So that means that this acceleration goes to 0. And so really what we can do is rearrange this and say that x minus x naught, so this is really just the change in distance in the x direction, equals to v naught times t. So this is just saying that delta x equals v naught times t, and so 100 meters equals v naught, which is what we're trying to find, times t. But the problem is we don't know how much time it takes for the ball to reach its end position there. So what we have to do is go back into the y component and think about something else. So for example, we know that the acceleration in the y component is just the acceleration due to gravity. So we can say that, again, moving this term over to this side, that the change in y equals v naught in the y direction t plus 1/2 g t squared. But we also know that this velocity, it only has an x component. So its y component, therefore, goes away and is 0. So what we're left with is that the change in y, which is 50 meters, equals to 1/2 times g times the time squared. And so if we use a calculator and plug in those values, so we say that 50 times 2 divided by 9.8 meters per second, which is the value of g, and then taking the square root of that answer, gives us that t equals 3.19 seconds. And so what we can do is we can plug that back into this equation here and say that 100 meters equals v naught times 3.19 seconds. And rearranging, we can say that 100 divided by 3.19 gives us a velocity of 31.35 if we round meters per second. And so that is how fast the ball was thrown off the cliff.